Welcome to ATMOS 5000 Day 39. We're focusing in on Chapter 12, Sections 12.1 and 12.2 from the Stull textbook. Today we'll be looking at the structure of anticyclones or high pressure zones, and we'll introduce the concept of an air mass, talk about how we classify air masses, and talk about how air masses are formed and how they move around the planet. So here we have a high pressure zone on the left with contours of the isobars. And on the right, we have a kind of a blow up of a portion of that high pressure zone. And marked with the squiggly line is the ridge. And we refer to that as a ridge because it's essentially a higher pressure. If this were a constant pressure map, then this would be higher heights. And that would be corresponding to a region of higher heights, which would be referred to as a ridge. So in the northern hemisphere, the winds are flowing clockwise around the high. In the southern hemisphere, they will flow counterclockwise around the high. But we still refer to both of those as anticyclones. And of course, a low pressure would be rotating the opposite direction in each of the hemispheres, and we refer to low pressures as cyclones. So one of the key factors associated with the weather and high pressure zones or anticyclones is the subsidence and the surface divergence. The surface divergence is what draws the air down from above to kind of fill that void, and it will actually lead to lack of clouds from the subsiding air, and it will also generally create a very strong temperature inversion at the top of the boundary layer. So here on the right, you can see that we have potential temperature versus height. In the boundary layer, in this well-mixed boundary layer, we have a potential temperature that is constant with height. That is the defining characteristic of a well-mixed boundary layer. And at the top of that well-mixed boundary layer, we have a significant temperature inversion where the potential temperature has increased quite significantly at that point. And this is really common associated with these anticyclones, these high pressure zones, where you have this subsidence. So an air mass is really just a widespread body of air that has similar temperature and moisture characteristics. And this large air mass will tend to adopt the temperature and moisture characteristics of the underlying surface. And the reason it does this is because air has a much lower specific heat than either water or soil. And so if you put cold air over a warm surface, the air mass is going to warm up from heat that is being derived from convection and conduction with the warm surface. And if you put a warm air mass over a cold surface, then the heat is going to flow from the air to the surface and the air mass is going to cool off. Likewise, if you put an air mass, a dry air mass over an ocean, the ocean is going to evaporate into that dry air mass and it's going to humidify it. And if you put a moist air mass over a dry air mass, you can get precipitation out of it, which would reduce the humidity of the air mass. So the common convention is that we define an air mass based upon its humidity and temperature characteristics. So for humidity, we basically have two descriptors. If it is a dry air mass, we tend to refer to it as continental because it was formed over the land. And if it's a humid air mass, then we refer to it as maritime because it was formed primarily over the ocean. And then we have different temperatures. So we have very cold temperatures, which we would refer to as Arctic. We have cold air masses formed in subpolar regions, which we would refer to as polar. And then we have warm air masses that are formed in the subtropical high, and that would be referred to as tropical. So we have Arctic, polar, and tropical. There are some other ones that are somewhat commonly used, but I'm not going to emphasize, and that would be equatorial, which is hot and formed near the equator, the monsoon, which is similar to tropical but very high in moisture, and then we have superior, which is a warm, dry air mass that originated aloft. And then we can also put modifiers on here, K and W. If the air mass is colder than the underlying surface, we'll put a K, and if it's warmer than the underlying surface, we could put a W. And then there are some special regional abbreviations. If it's an Antarctic air mass, it would be abbreviated as AA. And if it's a returning air mass, so we could have a polar maritime air mass that comes back to Britain, that would be a returning air mass. And we can also have layered air masses as well, if they are different air masses atop one another. So that's kind of the entire palette of air masses. And where do they typically form? So here we have the abbreviations. So CA would be continental Arctic, MP would be maritime polar, MT would be maritime tropical, CT would be continental tropical, and you can see that these air masses, the polar air masses, tend to form over the land surfaces in the northern hemisphere, the continental polar. That would be over North America and over Asia. Then we have our maritime polar air masses. In the northern hemisphere, those are primarily forming over the North Atlantic, the northern Pacific, but they also form over the Southern Ocean in the southern hemisphere. And then we have our maritime tropical, which is basically all of the rest of the oceans. This particular chart shows maritime equatorial, but many meteorologists just refer to maritime equatorial and maritime tropical as the same, and they just label them all as maritime tropical. And then the continental tropical are actually one of the rarest air masses, and that is a very hot, very dry air mass that's most common in the desert southwest of the United States, over the Sahara, and over Australia. So what I'm going to be emphasizing is a simplified air mass classification system that just uses these 5 different air mass types. We have Arctic, which is extremely cold and dry, maritime polar, cold and moist, maritime tropical, warm and moist, continental polar, cold and dry, and continental tropical, warm and dry. And if we look at how these air masses typically move, let's start off in the Gulf of Mexico, southwest of Florida. We have maritime tropical air masses that are forming over the warm, humid ocean, and these will tend to move northward into the eastern United States. And generally, those particular air masses generally do not cross the Rocky Mountains, and so the maritime tropical air mass from the Gulf and from the Caribbean basically only affect the eastern half of the United States. On the western half of the United States, if we do get maritime tropical air masses, that's typically during what we call the monsoon season, when we get flow from that region up to the southwestern United States. That typically happens in July and August each year. Otherwise, that air mass is fairly rare in the southwestern United States. We have maritime polar air masses that are forming over the North Pacific, and they're always coming on shore somewhere. If they come on shore in southeastern Alaska, then you get a lot of rain and precipitation up there. If they come ashore in the northwestern United States, then it impacts the Cascades and the Olympic Mountains. And if it comes on shore in California, it affects the Coast Range and the Sierra Nevada. We have continental polar air masses, which form in the central Canada, and they tend to move south along the eastern side of the Rocky Mountains and move all the way down into the Midwestern US and sometimes all the way down to the southeastern United States. We can also have Arctic air masses, which are forming even north of Canada, that can move further south, and sometimes those make it all the way down into the eastern half of the United States as well. I like to think of an Arctic air mass as an air mass with temperatures below 0 degrees Fahrenheit, so very cold. And then lastly on this one, we have maritime polar air masses, which are forming over the North Pacific, the North Atlantic. and then they come back into the northeastern United States from a northeasterly direction, and these are often referred to as northeasterlies. So how long does it take an air mass to form? So here we have an example of a cold air mass that was put over a warm surface. So we have a potential temperature of the surface, which is 20 degrees C, and the initial temperature of the air mass was 10 degrees Celsius. So it's 10 degrees colder than the underlying surface. And so as we march forward in time along the x-axis, you can see that after about 7 days, we're pretty much about 85 to 90% of the way to the temperature of the underlying surface. And to make it all the way to the temperature of the underlying surface would take about 2 weeks. So if you have a stagnant air mass that sits over a underlying surface for 5 to 7 days, you're pretty much going to adopt the characteristics of that underlying surface fairly quickly. And then what this figure also shows is that once the air mass has formed, and as it's exposed to the underlying surface longer and longer, the height of that boundary layer will increase over time, so that the heat energy from the underlying surface is either being added to or removed from an ever deepening layer of the air mass. So air masses tend to get deeper over time.